Hi, in this video, I'm discussing a question related to hydrostatics of fluids, and the question is shown on the screen now. A narrow, uniform circular tube is kept on a vertical plane, and half of its volume is filled with equal amount of two different liquids, X and Y. The density of X is rho, and the density of Y is sigma. Uh, The line drawn from the center of the tube, which is O, to the common surface of the liquids is making an angle theta with a vertical line drawn through the center O. So the question is, show that theta equal tan inverse sigma minus rho over sigma plus rho. Okay, we know that the liquid pressure is due to the weight of the liquid column. Okay, for example, if a vertical tube which consists of liquid of density rho to a height h means the weight of the liquid column is given by, volume of the liquid column, that is cross-sectional area, into height, that is the volume, into density, that is the mass, into g weight. So pressure at the bottom is given by pressure equal force over area. If you divide this by area, you will get h rho g, where h is the height of the liquid column. Height means the vertical height of the liquid column. Already the tube is in vertical position, so the length of the liquid column will be the vertical height. Right. Now when you keep the tube at an angle, here the weight of the liquid column is given by the length of the liquid column into area of cross section. If I say the area of cross section here also capital A, so that will be the volume of the liquid column. So A into L gives the volume, into density gives the mass, into G gives the weight. So the weight will act. Okay, so the pressure at the bottom is given by force over area. Force is the weight, so H rho G. Right, if the tube is kept at an angle, the length of the liquid column inside the tube is L, then the weight is given by A L rho G, where A into L is the volume, into density, into G. That's the total weight of the liquid column. The weight will act vertically downwards. So the force on the bottom will be the component of the weight along the tube downwards. That will be mg cos 90 minus theta. You know cos 90 minus theta is sine theta. So that will be mg sine theta. mg means al rho g. So substitute here mg al rho g. Rearrange it. A rho g into L sine theta. You know that L sine theta is the vertical component of the length of the column, that is h. So L sine theta is the vertical component of the length of the liquid column, which is h. So then finally the force on the bottom is given by AH rho g along the component of the force along the length of the tube. So the pressure at the bottom is force over area. That will be, if you divide this by area of cross section, that will be H rho G. Okay, so here the length of the liquid column is L, but the pressure acting on the bottom of the tube is given by H rho G, where H is the vertical component of the length of the liquid column. Okay, so these two are tubes with straight line. They are straight tubes. So students have confusion how to find the pressure exerted by a liquid column inside a curved tube, something like this, a curved tube inside it. So how to find the pressure exerted by a liquid column inside a curved tube. Okay, now I'm going to explain how to find the pressure exerted by a liquid column inside a curved tube. Okay, so a curved tube consists of liquid of density rho. The area of cross section of the tube is A. How to find the pressure exerted by the liquid inside this tube at the bottom of the tube. Okay, so I'm going to explain like this. We consider tiny length segments. How to find the pressure? Now, for example, imagine a pressure acting at this point. Actually, it's a tiny length. Consider tiny length delta x of the liquid column. Tiny length, but I'm showing it as the big length. But consider tiny length of the liquid column, but I'm drawing it as a big length. So tiny length. So that tiny length will be look like, even if the tube is a curve, a tiny delta x looks like a straight line. So delta x1, this length of liquid column will exert pressure at this surface. So what is the pressure here? I can say the vertical height of this tiny length liquid column could be delta H1. So pressure here I can say P1 is equal to, I already explained, if the tube is slope, we need to consider the vertical component of the length of the liquid column inside the tube. So P1 is equal to delta H1 rho G, that is the liquid pressure at this surface due to this tiny length delta x1. Its vertical components delta h1, I can call it as P1, the pressure at this surface. Similarly, what's the pressure at this surface? Imagine this length is very small, delta x2 I am calling. So if it is a very small length, even if the tube is a curve, it will look like a straight line, a small length, tiny length. That is delta x2. It looks like a big column. I'm drawing it like that. Otherwise, you can't see it on the board. So actually, delta x1 could be almost equal to 0, but not equal to 0. Almost equal to 0, not equal to 0. Same way, this length also, delta x2, almost equal to 0, but not equal to 0, right? Tiny length. So this vertical height will be delta H2. So the pressure at this point, the liquid pressure here will be this liquid pressure plus the pressure due to this length of column. So I can say P2, that is the liquid pressure at this point. P2 is equal to P1, that is the pressure due to this length of liquid column, plus the pressure due to this length of liquid column, that is delta H2 rho G. So P1 is equal to delta H1 rho G plus delta H2 rho G. So I can say delta H1 plus delta H2 rho G. That is the pressure at this point. Delta H1 plus delta H2, note down here, delta H1 plus delta H2 is the vertical height above this line up to the top surface of the liquid. Okay, what is the pressure here? So again, consider a tiny length delta X3 here, tiny length delta X3. So this height will be delta H3. Same way if I write it again, so I don't need to explain again. So P3 will be equal to P2 plus delta H3 rho G. Instead of P2, if I substitute delta H1 plus delta H2 rho G plus delta H3 rho G. So it's going to be delta H1 plus delta H2 plus delta H3 rho G. What is it? Delta H1 plus delta H2 plus delta H3 is the total vertical height above this surface up to the top surface, the most top surface of the liquid column. Okay, so like that, what will be the pressure here? So we need to consider delta H1 plus delta H2 plus delta H3 plus delta H4, delta H, like that. I need to consider all the vertical heights. If I consider the final pressure at this point is given by delta H1 plus delta H2 plus delta H4 plus dot 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 rho G. So these all heights, if I add, that will be the vertical height above the bottom surface up to the height of the top surface of the liquid column. So that will be H rho G. Okay, so that's the way we find it. The liquid pressure inside a curved tube is also given by H rho G, where H is the vertical height from the bottom surface where we are finding the liquid pressure from that surface to the top surface of the liquid level, the vertical height times density into J. Okay, I'm going to use this idea to answer this question. Okay, so here to find the pressure on the at the common surface due to the liquid X, I need to find the vertical height of this upper surface above the common surface. So I'm removing this. We know that is liquid X. So I'm raising this part. So I need to find that height above that level. I can call this height Hx, that is the height due to liquid X. The radius of the uh, circular tube, I can take it as R, and we know that half of the tube is filled with equal amount of two different liquids, X and Y. That's the way the question is saying. So half of the tube is filled when we consider both X and Y. So X and Y are having the same volume. So this length must be equal to the length of the liquid Y must be equal to length of the liquid X. So the common surface, from the common surface, if you draw a line to the center, you know this is a diameter. This length is equal to this length, means this point is the center of half of this circumference. This point is the center of half of this circumference. Therefore, this angle will be 90 degree. This angle will be 90 degree. I will take the radius of the tube as R. I'm going to make an adjustment. Here, I'm going to draw a horizontal line here. If I draw a horizontal line, this is vertical line, this is horizontal line. So this will be 90 degree. This is theta, means this angle 90 minus theta. So this angle, this angle will be, I can mark this angle will be theta, because this radius, which is a diameter, and this line, the line drawn from the common surface to the center, are 90 degree. This is 90 minus theta. So this angle will be 90 minus theta. That will be equal to theta. So this angle is theta. So Hx is the height of the top surface, the free surface of the liquid X above the common surface. So, okay, so I need to find Hx. So H is equal to this height. I need to find this height. I'll mark it with black ink. This I can call H1, this height, H1. Then I need to find this H1. So then I need to find this height H2. You can see that this height H2. So this is H1. Then this height from here to here, H2. This height is H2. So I'll remove this one. Yeah, okay, I'll keep this and mark this as H2. Okay, so Hx is equal to H1 plus H2. When we consider H1 in this triangle, consider this triangle, in this right angle triangle, the radius is R. So H1 is equal, in this triangle, H1, this height is equal to R sine theta. Same way, here if you consider this length in this triangle, this is radius r. So this h2 is equal to, in this right angle triangle, r cos theta. So that will be r into sine theta plus cos theta is hx. So pressure due to liquid X at the common surface, Px is equal to, the vertical height into density into G. I already derived it. So that is Hx rho G, that is R sine theta plus cos theta rho G. The total pressure, you have to add the atmospheric pressure. I'll say PA, the atmospheric pressure, because here could be air. Nothing is mentioned, so I can say this is air. If there is air, not a vacuum, then the atmospheric pressure should be added with the liquid pressure. That will be the total pressure at the common surface due to liquid X. Okay, same way I need to find the pressure due to liquid Y. So I need to find the vertical height of the liquid Y. Okay, so I need to find the vertical height of the liquid Y, the top surface of the liquid Y above the common surface. So that is this height, I need to find it. So this height, I need to find it, HY. HY, I need to find it. How much is that HY? Okay, so you can see HY is from this height. So I can draw a horizontal line here also. HY means this height from O to this point. So this length, this is 90 degree because in this right angle triangle. So this length minus this length is HY. So I can call this height from here to here. Too much of lines are there, but anyway, I can call this length H3 and this length H4. So HY is the vertical height of the free surface of liquid Y above the common surface. So I can say HY is equal to this height from the center to this point. This height, that is H3, minus this height in this right angle triangle, this height H4. What is H3? So consider this right angle triangle, this O, this right angle triangle. When I consider, this is radius R, this is radius R. So this H3 is equal to R cos theta. H4 in this right angle triangle, H4 is equal to, this is radius, this is theta, means this also theta because similar angle. This is the same line, this is horizontal line, this also horizontal line, this is theta, I already proved it. So this also theta, so H4 equal R sine theta. So pressure due to liquid Y, that is Py at the common surface, is equal to Hy sigma G. Sigma is the density. That is, instead of Hy, I can substitute this one. I can take the R common. R cos theta minus sine theta sigma G. And the total pressure at the common surface is given by plus atmospheric pressure due to the air column inside PA. Okay, so but at the common surface, the pressure due to liquid X, the total pressure due to liquid X must be equal to total pressure due to liquid Y. So I can say at the common surface, Px is equal to Py. So Px is equal to R sine theta. Or I can say, I can take the R common, R into sine theta plus cos theta rho G plus PA, atmospheric pressure. That is equal to R cos theta minus sin theta sigma g plus PA. So you can see that in this equation, PA and PA, the atmospheric pressures will get cancelled. R and R will get cancelled. G and G will get cancelled. So finally you will have rho into sin theta. I'll write it here. Rho sin theta plus rho cos theta equal sigma cos theta minus sigma sin theta. Divide the whole equation by cos theta. So rho into sin theta divided by cos theta plus rho. I'm dividing the whole equation by cos theta equal to sigma minus sigma sin theta over cos theta. We know that sin theta or cos theta equal to tan theta. So rho tan theta plus rho equals sigma minus sigma tan theta. Bring it to the left. Rho plus sigma tan theta. I brought this to the left. So rho plus rho tan theta plus sigma tan theta. I took the tan theta common. So rho plus sigma tan theta is equal to, bring it to the right, sigma minus rho. So tan theta equal sigma minus rho over sigma plus rho. So theta equal tan inverse sigma minus rho over sigma plus rho. That's the question.